Okay, we see here that the Hubble telescope is orbiting at 5.96 times 10 to the fifth meters above the Earth's surface. What is the period and the speed of the telescope? So if we look at this thing is orbiting around the Earth. Okay, we know that the force of the Earth is pulling the telescope on the Hubble. So if we look at this, Newton's second law will tell us that gravitational interaction of the Earth and the telescope divided by the mass of the telescope will equal the circular acceleration, since it is orbiting in roughly a circle around the Earth. Alright, and solving for the speed and the period, we can start dividing things out here. We see that the mass of the Hubble telescope can divide out. We can see that one of the radii of the Earth divide out. Looking at this, we get g times mass of the Earth divided by r is equal to v squared. This will allow us to solve for the speed of the telescope itself. So v, take the square root of both sides here, we get g times mass of the Earth divided by r. Okay, if we make that calculation, we are going to find out that, so g is going to be 6.67 times 10 to the negative 11th. The mass of the Earth is going to be 5.97 times 10 to the 24th. And then r here is going to be the distance to the telescope from the center of the Earth, which means we have to take into account the radius of the Earth and the altitude the Hubble is at. Okay, so over here we'll make that quick calculation. The radius of the Earth is 6.38 times 10 to the 6th meters. Okay, and the altitude in this case is going to be 0.596 times 10 to the 6 meters. So when we add the two, we get our little r to end up being 6.896 times 10 to the 6 meters. So when we substitute this in here for r and calculate, we are going to get 7,610 meters per second. That'll be our answer. Alright, so now they want to know what the period is. I can do a couple things here. I'm going to run from Newton's second law. We know that the speed when you're in a circular orbit will be the distance that the satellite travels around the Earth. That distance would be the circumference at little r, so 2 pi r, divided by the time it takes to make one complete orbit, which is capital T, which stands for the period. Okay, we see that this is squared in the equation, so we're going to square everything here. This will equal 4 pi squared r squared over t squared. Okay, now they're asking for the orbital period, so we need to have t and we need to bring it up into the numerator, which means looking at r and the denominator on one side and t squared on the other side. If we multiply both sides by r and both sides by t squared, we will get the following: t squared times g times the mass of the Earth will equal 4 pi squared r cubed. Okay, to get t squared by itself, we divide by capital G, the gravitational constant. These two will divide out here. We're left with t squared is equal to 4 pi squared r cubed divided by g times the mass of the Earth. Take the square root of both sides. We have t is equal to the square root of 4 pi squared r cubed divided by g times mass of the Earth. Take the square root of that. Alright, so 4 pi squared should give you 39.6. We cube 6.876 times 10 to the 6 and divide by 6.67 times 10 to the negative 11th, big G, times the mass of the Earth, which is 5.97 times 10 to the 24th. Once you calculate this, you find out it takes 5,685 seconds, which is about an hour and a half. Alright, that would be your answer for the period.